Hello, everyone. Let me know if you can hear me. Or at least one person can let me know if they hear me. Okay, excellent. All right. Thank you, everyone, to who showed up. Very kind of you. So I was thinking about what kind of content to cover for today. Hold on, let me just full screen myself for a moment. So I think basically on these streams, we're going to follow like two tracks. One track will probably be more interesting for computer science folks, people who want to program things, do interesting like machine learning algorithms and stuff like that. And the other track will probably be more interesting to people who, kind of like geometry or are thinking about relativity or, are interested in like specific parts of mathematics that require essentially like a heavy use of analysis and calculus. So for today's stream, I was thinking we could start by reading a calculus textbook. Now, just keep in mind, I'm sure at least some of you have taken calculus before, but the thing is, most of the high school calculus courses that you see, they only could cover calculus to a certain level, so they don't really do any of the calculus that involves linear algebra. So they don't really do any of the kind of advanced stuff, any of like the advanced multivariate stuff. And this is a big problem, actually, both for people who want to get good at physics and also people who want to get good at machine learning or anything like that, because you need to understand multivariable calculus in a way that kind of assumes linear algebra a little bit and a lot of like advanced mathematics in order to succeed. So the book I was thinking of starting with, and there are many options for advanced calculus textbook, but the book that I was thinking of starting with was this book called Hubbard. Let me put it up on the screen in case you would like to buy a copy. Let's see here. Here is the book. So this is the book that I learned calculus out of. Well, this is the book that I learned like advanced calculus out of. And what I really like about this book is that it covers like a little bit of linear algebra, also differential forms as well. So it'll help you prepare very well for anything you might want to do in the future. And another thing I really like about this book is that even though it like dips into analysis a fair amount, if you're not interested in learning that much analysis, you can kind of ignore that part of the book and just keep on going. So I was thinking for today's stream, we can discuss a couple of the sections right at the start. So I was actually thinking about the sections for real numbers, infinite sets, and complex numbers. Let me know if you have any preference for what to start with. I was thinking about going with infinite sets to start with. Just because, infinite sets are fun to think about. So let's just get started with stuff about infinite sets. Let's see here. Unless, like, anyone has, like, a very strong preference to start with something else. So let's see. Okay. So when we study sets, right, a big question is whether or not two sets are the same size, right? In fact, that's probably one of the most basic questions you can ask about two sets. And for finite sets, it's a pretty easy question to answer. So for example, if you have two sets, one consists of like, ABC. By the way, this is the notation we're going to use for sets. It's going to be a curly brace to open. I write them as squiggles, but I should be writing them like this. And so this set is a set that contains three elements. And for example, if you take the set 1, 2, 3, it's pretty easy to see that these two sets have the same number of elements in them. It's not too surprising. Another way to think about whether or not two finite sets have the same number of elements is whether or not you can kind of construct a function from one set to another that has certain properties. So for example, let's say I take a function f, right? What f does is it assigns a to 1, and let's say it assigns b to 3, and it assigns, let's say, c to 2. Now, this function is what's called a one-to-one correspondence between these two sets. And whenever you have a one-to-one correspondence between two sets, it's easy to see that they are of the same size. Now, the neat thing about finite sets is that, you can actually take this one-to-one correspondence understanding and extend it from finite sets to infinite sets. So we'll actually say that two infinite sets have the same size or same cardinality. Cardinality is the fancy word for size. Let me write it down. Cardinality. Okay, so two infinite sets, we're going to say, have the same cardinality if there is a one-to-one correspondence between them. So let me write that down too. 1-to-1 correspondence. Okay, so the idea is, and by the way, the word you have to add the word one-to-one correspondence at the end. The word one-to-one in mathematics and the word one-to-one correspondence mean slightly different things. So if you are talking about two sets being of the same cardinality, make sure you say one-to-one correspondence and not just the word one-to-one. But hopefully the idea, intuitively at least, makes perfect sense, right? You assign each element in one set to an element in the other set. And so what are the properties of a one-to-one correspondence? By the way, another word for a one-to-one correspondence is the word bijection. You'll see this a lot in mathematics as well. In fact, you might see bijection more often than you see one-to-one correspondence. So the idea of a one-to-one correspondence is, another word for it is a bijection. So one thing is that you want a bijection to have two properties. So this word bi over here, let me just color this red. This prefix bi over here is meant to refer to the fact that we want the bijection to have two properties. And the two properties we want it to have is that we want it to be injective, and we want it to be surjective. What do these two words mean? What do the words injective? What does the word injective mean, and what does the word surjective mean? The word injective means that you don't want two things on the left mapping to one thing on the right. So, for example, if I had instead defined the function like so if I had done it like this, let's say A and B both go to 2, and C, let's say, goes to 3. This particular function would not be an injective function because A and B both map to the number 2. So because A and B are both mapping to the number 2 in this case, we would argue that this function is not injective. Let me give you another example of a non-injective function between two finite sets. So let's say you have go back to the white pen. So let's say you have two sets. The first set is, let's say, A, B, C, D. The second set is maybe 1, 2, 3. Once again, it's perfectly possible to construct a function between these two sets that is not injective. For example, you could map A and B to 2, and you could map like C to 1, and you could map D to 3. So this is, again, an example of a function that is not injective. However, it's a perfectly well-defined function. It's just not injective. So as you can see, A and B are both mapping to 2 over here, which is making this function not injective. The other word is surjective. So surjective is asking the question, does everything on the right get mapped to? So let me just draw an example of a function that's not surjective. So let's say it were A, B, C, D, and maybe it's like 1, 2, 3, 4. So this is the domain is A, B, C, D, and the range is 1, 2, 3, 4. So for example, something like this is not surjective because the number 4, you see, is not getting mapped to. Okay? So this would be an example of a function that is not surjective. And this would be an example of a function that is not injective. Once again, a function is not injective if two things in the domain map to the same thing in the codomain. Okay? And a function is not surjective if something in the codomain does not get mapped to. Let me know if there are any questions about this. Actually, I'm not really used to it. This is my first time streaming ever, so I'm not really sure how much delay there is between the questions I ask and like chat to respond. So I don't know. I guess I'm just going to keep going forward. Just let me know if there are any questions. So the idea of a bijection is very simple. A function between two sets is bijective if it is both injective and surjective. So injective plus surjective means bijective. Okay? Now, the thing about a bijection is that we will consider two sets to have the same. So codomain. Good question. So the domain is the thing that you are mapping from. So it's where, you know, these ABCDs live. Okay, and a codomain is the thing that they are mapping to. So like 1, 2, 3, 4. So this is this would be a bijection between these two sets. Now, some people use the word range as well, but the issue with range is that it can be slightly confusing for some people. So some people use the word range interchangeably with the word image. So what is image? Okay, this is a little confusing. Image is everything that gets mapped to by the function. Okay, so the image here in this case would be 1, 2, 3, 4 because 1, 2, 3, 4 are all hit by ABCD. Okay, if instead I had defined this function like so, let's say 1, 2, 3, 4, but let's say A and B map to 2, and let's say C maps to 3, and D maps to 4. So the codomain of this function is 1, 2, 3, 4. However, the image of this function is just 2, 3, 4, because 2, 3, 4 are what is getting mapped to. And the reason I don't favor the word range is sometimes people use the word range to refer to the codomain, which is everything that can be mapped to. And they use it interchangeably with the word image, which is everything that is mapped to. Okay? So you'll find in like a lot of math papers, people prefer to use the word codomain because there's no confusion there. So just to say it another way, codomain is everything that can be mapped to. Image is everything that is mapped to. Okay? Let me know. Hopefully that makes sense. And once again, I'm still not used to the delay, so I'm just going to keep going. And if any question pops up, I'm happy to answer it. So we will consider two sets to have the same size if there's a function between them. Image equals codomain if surjective. Yes, that is correct. Good job, Almus. So what was I talking about? Yes. So now here's the thing. If you have two finite sets, okay? So if you have two finite sets, let's say A is a finite set, B is a finite set, and let's say A is like A, B, C, D, and B is like, I don't know, 1, 2, 3, 4, right? So if you have two finite sets, you can actually check if they're the same size if you have either an injection or a surjection. Okay? You actually only need to have one or the other because, and I want you guys to think about this if you can, if you have an injection between two finite sets, right, then that injection So what are we talking about? So, oh, I'm sorry. If you have an injection between two finite sets of the same size, I misspoke. Sorry about that. If you have an injection between two sets of the same size, it is automatically a surjection. Okay? So let me say what I was trying to say more clearly. I feel like I said it in a confusing way. Let's say you have two sets, A and B. Okay, and A is the domain of a function, and B is the codomain of a function. Okay, now let's say there is a function f from A to B, and let's say f is an injection. Okay, if f is an injection, you automatically know that the size of A. This is the notation I'll be using for the size of A. So the size of A is definitely going to be less than or equal to the size of B. And once again, I'm assuming that A and B are finite. A and B are finite. Sorry for the mess up earlier. But f from A to B, A and B are both finite. If f is an injection, then you know for sure that the number of things in A has to be less than or equal to the number of things in B. Hopefully that makes sense, because if f is mapping everything in A to something different in B, right? Remember, a function is injective if two things cannot map to the same thing, right? So if f is an injection between two finite sets, then you automatically know that the number of elements in A has to be less than or equal to the number of elements in B, because two things can't map to the same thing. Everything in A has to map to something different in B, so B must have at least as many elements as A. Does that make sense? Well, you can't answer immediately. Similar energy. So let's say you have f from A to B. Now let's say A and B are again finite. Are finite. So they only have finitely many elements in them. They're not infinite sets. And let's say that f is a surjection. Okay. A or B are finite, f is a surjection. Then you know that the size of A has to be greater than or equal to the size of B. Hopefully that makes sense as well. So if f is a map from A to B, and A and B are finite sets, and f is a surjection, then that means that the size of A has to be greater than or equal to the size of B, right? Because everything in B gets mapped to, right? Every single thing in B gets mapped to. If everything in B is getting mapped to, it's getting mapped to by something in A, right? Which means A must have at least as many elements as B. Hopefully that makes sense. This is why we consider, so we're trying to kind of extend this intuition from finite sets to infinite sets, which is why whenever there's a bijection between two sets, we consider them to have the same size. Because you see, if you have a bijection between two sets, remember, a bijection is both injective and surjective, right? So you have, let's say, f from A to B. Let's say A and B are finite. Right? F from A to B, A and B are finite sets. And let's say now that f is a bijection. Okay. So f is a bijection. That means f is injective, which means that the size of A is less than or equal to the size of B, right? And f being surjective means the size of A is at least as large as the size of B. You put two and two together, you get that the size of A is actually equal to the size of B. And this is why bijections give you a good notion of size. And what we're going to do is we're just going to take this notion of size and extend it to sets that are not finite. Okay? Now, this is where things get very interesting. If you have a moment to comment, bijective sets are therefore always equal. Careful now. we'll say bijective sets have the same size, but it doesn't mean that the sets are equal. So we'll say two sets are equal if they have the same things in them, okay? So for example, these two sets are equal because they have literally the same things in them, okay? Bijective sets are we're only considering bijective sets to be of the same size. We're not considering bijective sets to be equal. Does that make sense, Jojo, Jory? Okay, I'm sorry, I can't read that. But okay, so we'll say two sets are literally the same. They are equal to each other if they have the same things in them. Okay, and we'll say if there's a bijection between the two sets, we're only considering them to have the same size. Okay. All right. Let's extend this notion to infinite sets. Okay. Now, for an infinite set, I can't just say, like let's say A were the set of all natural numbers. Like let's say A were like let's see. Let's say A were the set 1, 2, 3, 4, going on forever, right? Then, if I say the size of A, I mean, you can say it's infinity, right? But I guess, let's say I were to include the negative numbers, right? Let's say B were all the integers, so it just goes from, like there's 0 in the middle, and then there's -1 and -2, and it goes off this way. And you have 1 and 2, and it goes off this way. It doesn't maybe you have to think a little bit harder about saying what the quote unquote size of A is. But we have this wonderful notion of when two sets have the same size, and we'll just carry it over. Okay, so I'm just going to say this is my definition. Okay, well, it's not my definition; it's a tale as old as time, but. So I'm just going to say, my fiat declaration, because it made sense with finite sets, I'm going to make my declaration that I'm going to consider. So I'm just going to say two sets have the same cardinality if and only if I can define a bijection between the two sets. Hopefully, based on everything I've said so far, and because this makes so much sense for finite sets, and also because I've drawn so many pictures of bijections at this point, hopefully this definition at least feels, in some sense, intuitive to you. Okay? So let's start by doing some examples. Now, before I dive into some examples, what I want to do is define some notation, because we're just going to be using this notation over and over and over and over again. So there are just some sets that pop up so much why only if? Okay. It's another bit of mathematical jargon. You will see this a lot. If and only if. So whenever you are making a definition, whenever you are saying, I am defining this to be that, you have to say if and only if, because you need the implication to go both ways. It is not automatic that the implication goes both ways. So for example, if I say to you, if it is raining, then it is cloudy. Or let me be even more precise. If it is raining, then there is at least one cloud in the sky. Okay? Then there is at least one cloud in the sky. I'm not a meteorologist, but one cloud in the sky. Okay, if it is raining, then there is at least one cloud in the sky. Okay? However, if I change this if to only if, the statement is now a false statement. So if I say it is raining only if there is at least one cloud in the sky, do you notice that's a different statement? Another way to see this is if I switch the order. What if I said if there is at least one cloud in the sky, then it is raining? So that's a false statement, right? So when you define things, and remember, we are making a definition. We are making a choice at this point, right? I don't know. I mean, technically, you could do your own math in a corner somewhere and think of another meaning for two sets to be of the same size, right? But we're following a tradition at this point, and I am defining two sets to be of the same size, right? If and only if there is a bijection between them, okay? So in other words, I'm declaring by decree, a decree made by many people throughout history, but this is my decree, that if I can find a bijection between two sets, they're of the same size to me, okay? And also, if I'm thinking about two sets that are the same size, I should be able to find a bijection between them, okay? So Praveen, I hope that answers your question. Okay. So could there be a possibility that there cannot be a bijection between two sets of the same size? Well, we're working with infinite sets now, so it is my declaration that I'm just thinking of two sets as being of the same size, of the same cardinality, when there's a bijection in between them. If you want to come up with your own separate version of size, go ahead. Then you'd have to develop your own kind of a logic, and don't apologize. Geez, please, yeah, everyone, just feel free to ask questions. I don't care. So this is my declaration, and in definitions, you always have to say if and only if, because you want the implication to go both ways. Okay, let me ask you guys some questions. So. Oh, sorry. Before I dive into the questions, there's some sets that kind of come up a lot when you're doing mathematics, so it's just good to have names for them. So the first is the set of natural numbers. Natural numbers are denoted with a blackboard N. So a blackboard N is, you just draw an N and then you put another line here. The reason this is called, let's see. So you're broadening the meaning of size to allow it to apply to sets that are less than, yeah, of course, that's literally exactly what we are doing, right? So so this bijection, we're hoping that it kind of extends things. Now I do want to say, hopefully you guys don't find this notion of two sets being bijective to be counterintuitive. Like you can imagine, a bijection is the ability to find a one-to-one correspondence between two different sets. Now, hopefully it's believable to you guys that if there is an injection and a surjection between two sets, that hopefully it also feels intuitive to you. Like, I said decree or whatever, but I'm hoping that it also feels intuitive to you guys that that really does mean the two sets are of the same size. Because, if you put them side by side, even if they're infinite sets, there's always a way to get from an element on one side to an element on the other side in a complete and total way. Okay. What are the natural numbers? So the natural numbers are all of the positive whole numbers. So, 1, 2, 3, and so on. Okay? So the natural numbers are one. By the way, if you take a computer science class, they will sometimes define the natural numbers starting at 0. It's just more convenient for them to work this way. All loops. Well, most computer languages, there are a couple out there that are not, but you'll notice all the array indexing, all the loops or whatever start at 0. So they also start their natural numbers with 0. Of course, I trained in mathematics, so I start my natural numbers at 1. It's not a big deal. Just use whatever convention is accurate to your field, and maybe mention at the top. If you're writing a paper or something, just mention at the top what convention you're using. Okay. Now the reason we use this boldface N, this it's called a blackboard N. It's just so that you don't ever confuse it with the letter N, right? People used to use like a bold N, but it's really hard to write a bold N on a blackboard. So people just started putting like an extra line through it, so it makes sense. Okay. So N, natural numbers, easy to remember. Z is going to be all of the positive and negative whole numbers. not board, like a blackboard, like chalk and blackboard that professors write on. So not board, but wow, board, blackboard, like the blackboard that teachers write on. Okay, so Z consists of all the negative and positive whole numbers. So you just it's a set I made earlier. So it goes -2, -1, 0, 1, 2, and then off. Okay, the Z is from the German word Zahlen, I believe. I don't know what Zahlen means. If there are any Germans here, please inform me. But actually, I think it's in Hubbard. Let's see what Zahlen is. It's in here somewhere. Oh, Zahl is just the German word for number, I guess. Pretty simple. Okay. So all the positive and negative whole numbers. Q is the set of all rational numbers. So this is, all numbers that I can write as a ratio of two integers as long as the denominator is not 0. Okay? So I'm going to actually do something now. I'm going to use what's called set builder notation. So by the way, this entire lecture is just like a, it's a way for me to sneakily introduce you to a lot of mathematical notation and ideas that you'll see in just a standard classroom, just so you don't feel unfamiliar with it. So I'm going to use something called set builder notation. You'll see this a lot. Okay, what is set builder notation? So set builder notation. So I was able to describe all the elements in the natural numbers and the integers using just this kind of list format, right? But you might want to, you might have a more complicated set that requires a more interesting, description. So in set builder notation, what you do is let me just explain set builder notation first. You'll say I'm defining my set S to be, and this is the format. You put the open curly brace, and you write it like this. You write stuff, then you put a line here. You read the line as such that. And then you write the properties that the stuff satisfies over here. Stuff that satisfies these properties. Okay, so this is how you write set builder notation. It's a really nice and concise way to write definitions of significantly more complicated sets. Also, I realize my face is covering. Whoa! I didn't mean to move my screen up. Hold on. Maybe I'll put my face up here. Okay, so stuff that satisfies these properties. So stuff such that these properties are satisfied would perhaps be the more grammatical way to say it. So I'm going to define the rational numbers using set builder notation. And maybe we'll try to get some more practice with set builder notation as well. So I can write the Q. By the way, Q is for quotients. I should have asked you guys to guess what Q stood for. So Q is all the numbers P over Q such that P is a integer, Q is a integer, and Q is not 0. All right, more notation for you guys. And this is why reading math can be so taxing sometimes, because you do need to. It's like learning a second language, but it's a really powerful language. You can get a lot of mileage out of it. But these symbols, this is in. Okay, so you just get increasingly concise ways to write things. So Q is the set of all quotients, so that the numerator is an integer, the denominator is an integer, and q is not 0. Hopefully that makes sense. Now R is the real numbers. I'm not going to define the real numbers right now. That is a very sticky question. Well, I don't know how long I'm going to stream for. We'll see what your guys' capacity is, or what my capacity is, to be honest. But R is all real numbers. C is all complex numbers. And we'll talk about both before I'm done today. Maybe we'll save it to next time. Okay, so N is the natural numbers, Z is the integers, Q is the rational numbers, R is all the real numbers, C is all the complex numbers. Don't you technically define the rational numbers with equivalence classes, or does that go too far right now, I guess? I'll talk about equivalence relations and equivalence classes. I don't want to belie... oh, by the way, thank you for the question, Nikki. So I don't want to... people already have a strong intuition about what natural numbers are, and I don't want to steamroll that. People already have a sense of it, and I'm just gonna try and ride that sense as far as I can before I dive into equivalence classes. We'll probably do for the computer science folks, especially, just a series on discrete math, and we're definitely going to be talking about relations and stuff there. So stay tuned. But I hope that answers your question. So these are very, very commonly used sets. Also, some more notation, since we're here. So let's say I have two sets, A and B. Okay. Let's say A is the set. Let's say A has in it A, B, 1 and 2. Let's say B is the set A, B, C, and D. Okay. So A union B is the stuff that is either in A or in B. So this is read union. Okay. So this would be A, B, C, D, and 1, 2. By the way, when you have a set, you can think of sets as like a bag full of stuff. All you care about is what's in it and what's not in it. It does not matter the order that you write things. Okay, a set is just like a bag full of stuff. The order that you write it doesn't matter. All that matters is what's in it and what's not in it. A intersect B is going to be all the stuff that the sets A and B have in common. So what do the sets A and B have in common? Just a lowercase a and lowercase b. So this is the intersection. Okay, hopefully that makes sense. So this is the union. This is the intersection. There's other stuff too. So A minus B is all the stuff that's in A but not in B. Okay, so this is a set minus. If you've programmed before, you've definitely used probably all of these, But union, intersection, set minus. So A minus B is all the stuff that's in A but not in B. What's all the stuff in A that's not in B? Well, A and B have lowercase a and lowercase b in common, so this would just be 1 and 2. Okay. Another thing to keep in mind is sometimes people write set minus like this. You'll see that sometimes, just with a slash like that. So don't get confused if you see this in like a paper or a math book or something like that. So this and this are both set minus. Okay, there's other stuff too, but we'll get into it when we get into it. I don't want to burden you too much with notation. That was a lot. So what was I talking about? Oh yeah, bijections and infinite sets. So, all right. I want to ask you guys a question. I'll actually wait for a response to this. Let's say I take the natural numbers, which again is 1, 2, 3, 4, 5, and so on. And let's say I took all the even numbers. So I'm going to be a little sloppy here. I'm just going to write 2 times the natural numbers, which you can read as I'm multiplying every natural number by 2. So, you get like 2, 4, 6, 8, and so on. Okay. Do you guys think there's a bijection between these 2 sets? And this will be a good chance for me to see how delayed everything is. As in, do you guys think that, according to the stuff that we've done so far, that these 2 sets are of the same size? Some creep says yes. It felt horrible to say. I've seen Vsauce, so I think so. Okay. Okay. And the answer is yes. So I will say, for most people, there is a sort of visceral sense that the even numbers there should be kind of fewer even numbers than there are natural numbers, because of course the set of even numbers is contained inside the set of natural numbers. Again, more notation. So this is a subset of. Okay. Just in case you haven't seen that before. And Nikki says that f of x equals 2x is a bijection, and indeed it is. So if you do just multiplication by 2, so if you multiply every number by 2, that defines a 1-to-1 correspondence between these 2 sets. So 5 would map to 10, and so on. Now, f of x equals 2x is an injection, because if for 2 natural numbers, so how would you prove this if you had to write it up? If 2x equals 2y, then that means that x is equal to y. Right? So if 2 numbers are mapping to the same number via this 2 times multiplication map, then those 2 numbers have to be the same number. Hopefully that makes sense. Also, every even number can be written as 2 times a natural number. Right? Every even positive whole number can be written as 2 times some natural number. So we have a bijection on our hands here. All right. Very interesting. What about... Oh, and please let me know if there are any questions about that. What about the natural numbers and the integers? All right, versus. Do you guys think these 2 sets have the same size? So remember, the natural numbers, in case you forgot, are 1, 2, and so on, all the positive whole numbers. And z is, all the way down to, then the negative numbers, followed by the positive numbers. And indeed, there is a bijection between these 2 sets. So how would you construct such a bijection? Well, the idea is fairly simple. You can list off all the integers like this. You can start at 0, right? Oh, I think the size of z is greater than the size of n. Once again, that feels very, very intuitive on some level, but if we're only thinking about bijections, we're only thinking about whether or not it's possible to make a list of one and the list of the other in terms of a one-to-one correspondence, it turns out it is possible to construct a function. Just watch. So we can have 1 mapped to 0, right? We can have 2 mapped to 1. We can have 3 mapped to -1. We can have 4 mapped to 2. We can have 5 mapped to -2. We can have 6 mapped to 3. We can have 7 mapped to -3, and so on. Now I want you to notice it's a simple enough algorithm, and it's injective because every integer, every natural number is going to a different integer. Hopefully that's clear. Every natural number is definitely going to a different integer. So this function, as I've described it here, is definitely injective. And you can also see that all of the whole numbers, all of the integers are being hit. There's no integer that will not eventually appear on the right-hand side, okay? Map all the even to the positives and odd to the negatives. That is what we did, right? So we're mapping, I guess except for 0, we're mapping even numbers to positives and odd numbers to negatives. Feels perfectly reasonable. Okay. Very, very good. Oh, by the way, if you're uncomfortable, some people, when they see a function like this, they really, they really don't like it. So you can write this function like this, f of x equals, let's see, x over 2 if x is even. And I guess x minus 1 over 2 if x is, negative of x minus 1 over 2 if x is odd. Of course, I'm covering up my own function definition. Let's see here. All right. Hopefully you can see that. And hopefully I defined it correctly. So let me just double check it. 5 minus 1. It looked like my stream dropped for a second. Hopefully you guys are still there. Okay. So interestingly enough, we've determined that the size of the natural numbers is equal to the size of, the even natural numbers, right? Is equal to the size of the integers. By the way, a set that's either finite or has the same size as the natural numbers, we will say is countable. Okay? Countable is finite or same cardinality as the natural numbers. Every infinite set we've thought of so far is countable. So far that I've listed on this list above, at least the natural numbers, twice the natural numbers, and the integers are all countable because I'm able to construct a bijection between the natural numbers and these sets. Now, I hope that this word countable feels good to you, like it feels intuitive to you. The reason we use this word countable is that any set that's countable, there's a bijection between such a set and the natural numbers, which means I can, make the natural numbers my domain for a function, list out all the natural numbers, just in a list as we usually do. And there should be some one-to-one correspondence between all the natural numbers and this random set that I'm considering. And so this idea that if a set is countable, there's some bijection between it and the natural numbers, which means, of course, that I can kind of list off every element in this infinite set. Of course, the list will be infinitely long, but hopefully the word countable feels good to you guys. Let's do another one. What about the rational numbers? Let's do the rational numbers versus the natural numbers. Do you guys think the rational numbers are countable? And I want to hear from people who haven't seen this before. Or, you know what, if you've seen it before, that's fine too. What am I saying? Do you guys think that the rational numbers are countable? Hipira says not. Okay. Any other guesses? I know the answer. Okay. I believe not. Abhivarma says, I believe not. Okay. I think that's all I'm getting, so I'm going to give it away. This one is extremely, extremely, extremely shocking, but it is true. The rational numbers are countable. Kind of insane. If this is true, it should be possible to kind of make an infinite list of rational numbers, right? So it should be possible to somehow, and it's kind of like, you know, you might think like, what, how? Like, how would you do this? It should be possible to just kind of define a bijection between the natural numbers and rational numbers. So it should be possible for me to make a list of all the rational numbers, and I should be able to justify to you that no rational number appears on this list twice, right? And I should also be able to justify to you that every rational number does appear on this list. Agreed? Okay. So, kind of interesting. But it is true that Q is indeed countable. Now, in order to prove this, I'm going to prove first another equally surprising fact. Okay? And then I'm going to prove a little theorem that really helps you check when two sets are the same size. Okay? And we're going to use that to show that Q is countable. Okay? So, first we're going to compare n cross n to n. Okay? First of all, if you've never seen this before, what is n cross n? So, n cross n is, so whenever you see two, like A, so if you see, like, let's say A is ABC, and let's say B is 1, 2. Okay? So, A cross B is going to be all of the ordered pairs you can make with the first thing in A and the second thing in B. Okay, so A cross B is going to be this stuff. It's going to be the pairs A, 1, and then B, 1, right? And then C, 1, and then A, 2, and then B, 2, and then C, 2. Okay, I believe I'm in my own way again. And last time I moved myself, the stream flipped out, but I hope it doesn't yell at me this time. All right, so A, 1, B, 1, C, 1, A, 2. So hopefully the definition of the product of two sets is making sense. And remember, I'm defining this in an effort to, how do you say? Showed you eventually that the rational numbers are countable. Okay, so you have A, 1, B, 1, C, 1. Okay, so n cross n versus n. This one should be equally surprising as the rationals one, but all ordered pairs of rational numbers, of natural numbers, this has the same cardinality as n. So n cross n is countable. Okay, a very odd one indeed. By the way, if you want to visualize n cross n, if you want to visualize the product between two sets, especially if there are sets of numbers, you can do it graphically. So if you draw n on the number line, so this is n on the number line, so it has it starts at 1 the way we're doing it. There's 2, there's 3, there's a 4, there's 5, 6, and so on. And so on it goes. This would be sort of a visual representation of what the natural numbers are. Okay? Now, what would n cross n look like? Okay. N cross n looks like this. You can represent it graphically like this. So 1, 1 would be down here. You can kind of fill in this grid like so. So this would be like 2, 1. This would be 3, 1, and so on. So this is a visual representation of n cross n. All right. Like I said, it's a lot like with the rational numbers. It really feels like there's way more stuff here than there is over here, right? It just feels that way, right? However, if the metric we're using for size is bijections, and once again, I've argued that this is a very reasonable way to decide if two sets are the same size, it is in fact the case that the natural numbers and ordered pairs of natural numbers are the same cardinality. They are the same size. So how would you do this? This is a little cheeky, but you can make your list like this. There are tons of different ways to do this, but I'll draw a picture for you. I'm just going to say 1 maps to this one. This is how I'm making my list. Okay, so 1 maps to 1, 1. Oh my goodness, I'm covering myself again. Hold on. There's just like there's no place to put my face. Hopefully that's okay. So 1 will map to 1, 1. So that's how I'm saying 1 maps to 1, 1. That's why I drew the red dot here. Okay. Now I'm going to say 2 maps to 2, 1. Okay. 2 maps to 2, 1. Okay. Just constructing my list in the red here at the top. Okay. Now I'm going to say 3 maps to this one, 1, 2. Okay. Now it is definitely possible to write down like a more official looking definition of what I'm doing, but basically you can hit every pair of natural numbers like this. Just draw a little sneaky little draw a sneaky little curve here, and it just does that. It's very nice. So 1 is mapping here, 2 is mapping here, 3 is mapping here, 4 is mapping here, 5 is mapping here, 6 is mapping here, 7 is mapping here, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so on. So, hopefully you see that I am indeed hitting every pair of natural numbers exactly once. So this function that I've drawn, I didn't write down like a full-on official definition or anything like that, but hopefully it makes sense. And let me know if it doesn't. But this thing that I'm drawing here, as you can see, it really does hit every pair of natural numbers. So this function, as I'm defining it, is truly surjective. And also, it's apparent, seems like the way you map decides if it's mappable or not? Ooh, that is a very interesting comment, Jojo, and I will return to it. I will return to it. So, but let's keep going with this. I will say, Jojo, your intuition about this is in line with the intuition of most people that thought about this before Cantor showed up. Okay, and then Cantor broke the game. So we'll talk about what happened when he came on the scene. But for now, hopefully it seems plausible and reasonable to you that I am indeed truly defining a bijection between pairs of natural numbers and natural numbers. Truly, every pair of natural numbers is hit by this map, and it's hit exactly once. Injective, surjective, bijection, done. Okay, and J55 is making the excellent comment that 1/2 is not the same as 2/4. So the strategy that I'm using to map natural numbers to pairs of natural numbers is simply not going to work for rational numbers because I won't get an injective function, right? So you might think here, and it does almost work, right? So you might think here, instead of writing 1, 1, why don't I write 1/1, right? And instead of writing 2, 1, why don't I write 2/1? And instead of writing 1, 2, why don't I write 1/2, right? Then this exact same strategy would give you a way to define, at the very least, a surjective map between the natural numbers and the rational numbers. Let me know if that makes sense. So this strategy, I hopefully you all agree with me that I pulled no shenanigans here. There really is a bijection between the natural numbers and pairs of natural numbers. And the idea is exactly what J55 is suggesting here, which is we can convert we're going to try and convert this strategy to rational numbers, because instead of using pairs of natural numbers, I'm going to quotient them, right? Instead of 1, 1, I'm going to write 1/1. Instead of 2, 1, I'm going to write 2/1. Instead of 3, 1, I'm going to write 3/1, right? And so in doing this, I will definitely hit every rational number. But unfortunately, using this strategy, I will certainly hit some rational numbers more than once, because, as noted, 1, 2 is you can think of as the rational number 1/2, and 2, 4 would then be the exact same rational number. So a good question at this point is, how do you get out of this? And there are many ways to get out of this, but I'm going to show you the most useful and powerful way to get out of it. First of all, let me know if there are any questions. Like, do you all find it believable now that pairs of natural numbers and natural numbers have the same cardinality? And if so, we can move on to the real meat and potatoes here. So let's see here. I always spell this person's name wrong, so I want to make sure I do it right. Okay. Schroeder. Bernstein. Theorem. Okay, so we're going to discuss the Schroeder-Bernstein theorem, which allows us to sneak out of the issue that J55 has suggested here. Okay, so it turns out that this is the Schroeder-Bernstein theorem. Okay, and we're going to prove this. So two sets have the, let me name the two sets just so that the theorem is even more clear. Let's say two sets A and B have the same cardinality if, so usually the next part, oh, hello Manoj. So usually the end of this sentence would be if there's a bijection between them, right? So two sets A and B have the same cardinality if there's a bijection between them. But I'm going to put a little spin on it here. So if there is an injection right, F from A to B, and an injection G from B to A. Okay? So, let me move myself out of the way here. Hold on. So, is math invented or discovered? I really want to know your thoughts on it. Maybe some other time. kind of in the middle of something right now. I'm actually, I'll say it. I'm very strongly in the discovered camp. But that doesn't mean anything. I mean, it's just a philosophical question. So, the Schroeder-Bernstein theorem. Two sets A and B have the same cardinality if there's an injection F from A to B and an injection G from B to A. An extremely, oh, hey, Brian. So an extremely, extremely, extremely powerful theorem. Notice this allows us to get away from having to prove that there's a bijection between the two sets. I only need to find injections going both ways. Okay? By the way, I can actually also replace the word injection with surjection here, and that's also true. So you can, this is also the Schroeder-Bernstein theorem. So if there's a surjection. First, let me convince you that this is intuitive, at least. And the easiest way to see that something like this is intuitive is to think about how it works for finite sets. Okay, let's just think about this for finite sets. So hopefully, the theorem itself makes sense. So I'm going to say, if I have two sets A and B, and I'm able to construct an injection between them going one way and an injection going the other way, then it should be possible to construct a bijection between them. Or if I can construct a surjection going one way and a surjection going the other way, then I should be able to construct a bijection between the two sets. Okay? Let's see if this is a plausible idea for finite sets. Okay. Let's say I have two finite sets. Let me stop writing in red. Okay, let's say I have two finite sets, A and B. Right? Let's say A and B are finite. Okay. Now, let's say you have a function f from A to B that is an injection. Right? Now, if everything in A is mapping to something different in B, then that must mean that the size of A is less than or equal to the size of B. Hopefully you all find that plausible. Now let's say I also have an injection G from B to A. That means everything in B is mapping to something different in A, which of course means that the size of B is less than or equal to the size of A. Notice less than or equal to, the way we've done it only makes sense to talk about this for finite sets. I don't know how to deal with less than or equal to if I have infinities involved. There is a way to deal with it, but some other time. So F from A to B is an injection, means that A is less than or equal to B. G from B to A is an injection, means B is less than or equal to A. This is true for finite sets. But of course, if A is less than or equal to B and B is less than or equal to A, that of course means that A is equal to B. So for finite sets, at least, it's easy enough to conclude that if I have an injection going both ways, then the size of A must equal the size of B. This is perfectly clear for finite sets. For infinite sets, however, you have to be a little bit more careful. So for example, it's possible to, for example, define, let's use the natural numbers and the even numbers as our example, okay? What I can do is I can define a map. Let's say, so these are our natural numbers, 5, 6. And then the even numbers are 2, 4, 6, 8, 10, 12, and so on. And I can use the same map that I used earlier, which is multiplication by 2, right? So actually, you know what? I'll do multiplication by 4. 2 times 4 is 8. 3 times 4 is 12. So this can be my map F. Okay, my map F going from left to right is multiplication by 4. So F is multiplication by 4. Okay, and G, I will say, going from right to left is, let's say, also multiplication by 4. Let's say G going from this way to this way is actually, you know, maybe I'll just make it. Yeah, let's say G is also multiplication by 4. And then, for example, 4 would map all the way down here to 16, and 8 would map to 32 all the way down here. And so for the infinite case, it's definitely not as clear what to do in this situation, right? So you have clearly, I hope you find it plausible that F and G are both injective maps. They definitely don't map two things to the same thing, right? Neither of them do. They definitely don't map two things to the same thing. But it's unclear how to use this, right, in order to actually define a bijection between the two sets. Right? So in the finite case, it's clear enough that if F is injective and G is injective, then it should be possible to define a bijection between the two sets. However, if the two sets are infinite, F being injective and G being injective does not in an obvious way give you some kind of bijection between the two sets. So how are we going to take care of this? Well, here's the idea. All right. So let's say that we're in our situation. You have A, you have B, and you have F mapping from A to B injectively, and G mapping from B to A injectively. So F from A to B is injective, and G maps from B to A, also injective. All right. So now, you have a list, everything in A, everything in B. Okay. So this is just a visual representation. Obviously, this can get very complicated. But let's say the stuff in A is like A, B, C, D, and so on, and the stuff in B is like 1, 2, 3, 4, and so on. What I'm going to do is divide this picture into into what I'm going to call chains. Okay, I'm going to divide this picture into chains. Okay, so far so good. So what's a simpler bijection from n cross n to n is f of a comma b equals 2 to the a, 3 to the b. I wish Minecraft player, but you'll notice that map is injective, but it is not surjective, because not every natural number has a factor of either 2 or 3. It may have other factors. So for example, this map would never hit the number 5, right? So It's not. Yeah, you do. Sorry, you do have to put in work, unfortunately. Though I do appreciate the comment. In any case, so f from A to B is injective. G from B to A is also injective. What I'm going to do is I'm going to use this to divide this picture up into chains. Okay, so these chains are going to be basically bidirectional sequences. Okay, they're going to be sequences that go off in either direction, and here's how it's going to go. So like, let's say A maps to 3 via F, and maybe 3 maps to D via G. I don't know. I'm making it up as I go. And maybe D maps to 2 via F. This is how I'm constructing these chains. I mean, you imagine you're just, you just write things. So for example, I could put, A here, right? And the next thing would be 3 because A maps to 3 via F, and then G maps it to D, and then F takes D to 1, right? So it's like a alternating. Wait, that's not a biject. Yeah, that's right. So it's like alternating, with an element of A and an element of B, and you basically travel from A to B via F, and you travel from B to A via G, right? You can construct chains like this, right? So a chain is a bidirectional sequence. So for example, if something mapped to A, so for example, I don't know, if 17 mapped to A via G, then 17 would come before A in this chain, okay? So these chains are, these infinite lists extending in either direction, right? And you move from one element to the other. So if it's in A, you move to the next one via F, and if it's in B, you move to the next one via G, and also in reverse. Okay? Hopefully that makes sense. So I'm divvying up this whole setup into these chains. Now I'm not using the word divvy up lightly. Now, here's the next thing I'll point out to you. These chains are disjoint. So if I take a chain, right? If I take one of these chains and I take another one of these chains, if they don't have, so if they have even one element in common, then they are the same chain. Okay? If they have even one element in common, then they must be the same chain. Okay? Otherwise, they're all completely separate from each other. These chains are disjoint. Okay? Hopefully that makes sense. So let me just try and prove that to you, first of all. Why would these chains be disjoint? Why would these chains be disjoint? So what would happen if two chains? So let's say you have let's say you have a chain. It goes like 1 F 13 Z 32 B and on, right? So this is one chain, right? And let's say you had another chain. I don't know. It's like a 2 Q 37, but it also has a Z in it, let's say, right? So 1, I don't know, C, and so on. So these are my two chains. So notice these two chains are not the same, but they both have this Z in common with each other. I'm trying to say that this is not possible. Something like this can simply not happen here. Any guesses as to why this is? Why could that not happen? Is it like a deterministic system? I mean, yeah, it's definitely, there's definitely no randomness in here. How is Z mapping to 32 and 1? Already a fantastic problem here. Z cannot map to 32 and 1. I agree completely. But that was a good comment by, slap a silly dog. Okay, thank you. So I agree. Everything after Z has to be the same. So C. Okay, but then why can't this situation happen? And someone else commented that, notice if you read this, it's saying that F, for example, G takes 13 to Z, and G also takes 37 to Z. This is bad because G was supposed to be injective. G cannot take two different things to the same thing, right? So this is just bad news, right? Chains, distinct chains have to be disjoint from each other. Hopefully that proof makes sense, but let me know if there's any part of it that doesn't. I'm happy to repeat it. Okay, so what we've established so far is the fact that the distinct chains are disjoint, right? So distinct chains are disjoint. Okay. So if I look at my two lists, you can imagine that there's like these these like chains going back and forth, but they don't ever contain the same stuff. Okay, they don't ever contain the same stuff. Also, there are three possibilities for these two chains. Okay, number one, a chain can go on forever in either direction. It's totally a possibility, right? A chain can go on forever. Chain can go on forever in both directions. Okay, that's a possibility. The second possibility, as you may have guessed, is a chain might terminate at some element of A that's not in the image of G. Okay, so terminate, I'll just say terminate in A, and I'll put in brackets, at some element. I'm running out of room. So I'll just say it out loud. Hopefully it makes sense. You can terminate an A at some element that's not in the image of G, or you can also terminate at B at some element that's not in the image of F, right? In B. All right. Hopefully that makes sense, that these are the only three possibilities that we are dealing with, right? A chain can either go on forever in either direction, or it can terminate in A, or it can terminate in B. Okay. So here's what we're going to do. Here's how we're going to take the fact that we have F and we have G, and we know that distinct chains are disjoint, and we know that these are the three possibilities, right? So we can use this to construct a map, an actual bijection. So I'm now going to construct a new function, okay? And the new function, here, let me move this over. Not completely used to using this program. Okay, you make sure I'm still visible. Okay, so let's see here. Wait, cancel. Wait, how do I leave the selection? Oh, deselect. Okay, perfect. So I'm going to define now a new function, okay? And I'm going to call this function h. Remember, the entire goal was we have an injection f from a to b and an injection g from b to a. So how do I construct a new function? So here's what we're going to do. I'm just going to say H is going to be defined as follows. H of A is just going to equal F of A, okay, if A is in a chain where 1 or 2 happens, okay? If A is in, I'll write the whole thing down, this is a lot. A is a chain in which 1 or 2 happens. 1 or 2 happens. Okay? So H of A equals F of A if A is in a chain where 1 or 2 happens. Okay? So H of A is going to equal F of A if the chain that A is in goes on forever, or if the chain that A is in terminates in A. Okay? What do you do otherwise? I'm going to define H of A to equal G inverse of A. So this is if the other possibility, else. Okay. So hopefully this definition for this new map H makes perfect sense. Okay? So H of A is equal to whatever F is sending it to, right? If A is in a chain in which 1 or 2 happens, and it's equal to G inverse of A otherwise. Okay? A rather interesting and curious definition. The claim is, of course, that H is a bijection. So H is a, well, actually, there's a couple things. H is a function, right? Number one, can't get out of that. We need to show H is a function. So in order to be a function, for example, it can't be mapping 1 input to 2 outputs, right? That would be very bad. And it's not entirely clear just by looking at this why 1 input would not be mapped to 2 outputs, okay? So first and foremost, H is a function, okay? Also, H is injective. Also, H is surjective. Okay. How are you guys feeling about this so far? I'm thinking about leaving this as an exercise to you guys. We can talk about it next stream or whatever in case everyone's having trouble. But I want you to think about why is H well-defined? Why is it a function? And also, why is H injective and why is H surjective? Okay. Now, just to it's really not that hard to see. We've already done all the hard work. Okay, so let's say you have some element A, right? And let's say H is mapping it to 2 different things. So you have some bad situation going on here. So here you have a F coming out of this and mapping it to some F of A, right? And here's some B that G maps to A, right? This would be an example that this would be an example of a bad situation, right? So here in this situation, A maps to both F of A and G inverse of A, which is equal to B. Now, the reason that this situation can't happen is because you only map H of A to F of A if A is in a chain in which 1 or 2 happens. So it can only happen in a situation where the chain continues forever, right? Or you have a chain that terminates in A, right? And G inverse of A otherwise. Okay, so that's my hint to you. I mean, I could go over it, but I don't know. Maybe it's good if you spent like a second. We've already done. I swear we've already done the hard work. I want you to take a minute to think about why is H a good function. For example, why can't this happen? This would be very bad. right? If A mapped to two different things. Also, you need to explain why this can't happen, right? So why can't two things map to the same thing? That would also be bad, right? And then number 3, you also need to explain why is everything on the right-hand side, why is everything in the codomain hit by this function h? Okay, it's not a particularly hard exercise, but I will leave it to you guys. Okay. So this is your homework. Let me know if like you guys just don't even want to do any work on the side. I can also just like prove everything. But hold on. I dead ass thought you were dead. No, I'm certainly alive. Some of the reason I got interested. Oh, thank you, Tens. It's very sweet of you. Okay, so assuming you finish the little bit of work, I swear it's just a little bit of work I left you at the end. In order to check that two sets are the same cardinality, all you need to check is that there's an injection going both ways between them. And I'll also leave it to you to check that you can modify the same argument to work if there's a surjection going both ways. Okay? I will tell you though, right now, that the fact that we now have this power, like all we need to show that two sets are bijective is, that there's an injection going both ways, or all that we need to show that two sets are, it's too hard, I can't prove it. Just give it more than a minute. I'm sure I swear it's not so bad. And if everyone hates it, I'll just prove it next stream. It's not a big deal. I just want to, I said like an hour ago that Q was countable. And I actually want to get to it, today. So, okay. So it turns out all you really need to show that two sets are bijective is two injections going both ways or two surjections going both ways, right? Which is a lot easier than actually constructing a bijection. So guess what? N cross N is countable. We already proved this. So since N cross N is countable, we showed this by actually constructing an honest-to-goodness bijection between the natural numbers and the pairs of natural numbers, right? So, the natural numbers. So we were able to construct a function from the natural numbers to the product of natural numbers that was injective and surjective. So we found an honest-to-goodness bijection, right? So we can actually send any pair of natural numbers, right? So let's see here. We can send like A comma B, right, to, let's say, A over B, right? We can map it to A over B. And this is going to be a map to the rational numbers, right? So, in fact, we can do this. We know there's a bijection between the natural numbers and the integers, right? And just in the same way that so that means there's a bijection between the integers and the integers cross the integers. Hopefully I'm not saying anything that's too crazy. So because there's a bijection between the natural numbers and the integers, there's definitely a bijection between the naturals cross the naturals, like pairs of natural numbers to pairs of integers. You can just use the product of these two maps. And so you have a bijection from the naturals to the naturals cross naturals, right? And that maps to integers cross integers. Okay? This leads to if you like, a surjective map to the rational numbers. Just you know, if the second number is 0, just send that to 1 always. You know, so but this will give you a surjective map. So this is a bijection, right? This is a bijection. So because there's a bijection between the natural numbers and the integers, there's a bijection between the naturals cross the naturals and the integers cross the integers, right? There's definitely a bijection here. Okay. And now there's also a bijection between the naturals and the naturals cross the naturals. So we have a bijection here. Right? So, you know, there's a bijection between the naturals and the integers cross the integers. Right? It's not hard at all to construct a surjection between the integers cross the integers and the natural numbers. So you can do a surjection here. You can just take p comma q and map it to p over q, unless q is equal to 0, right? If q is 0, just map it to 1, right? If you see like p comma 0, just map that to 1. I don't care. This is a terrible map, but it's a surjection. Every natural number, every rational number will for sure be hit by this map. And let me just erase some things just to make it clear. So now we have a surjection going from the natural numbers to the rational numbers. Pretty wild, huh? So we have a surjection going from the natural numbers to the rational numbers. Wild. It's not hard at all from this point to construct a surjection going from the rational numbers to the natural numbers. So how might you construct a surjection from the rational numbers to the natural numbers? Well, you know, the rational numbers just contain the natural numbers, right? So, you know, you can map each natural number to itself and map every other number to 1. Right? So there's a perfectly good surjection here. So we were able to construct a surjection from the natural numbers to the rational numbers. And we were also able to construct a surjection from the rational numbers to the natural numbers. Please, please, please let me know if there are any questions about this. I know that this was a lot. So just, you know, pause me if any of this at all does not make sense. But I was able to construct a surjection between the natural. So I constructed a well and good bijection between the naturals to the naturals cross naturals. And that led to a surjection to the rational numbers. And then from the rational numbers to the natural numbers, there's also a surjection. Because there's a surjection going both ways, we know these two sets have the same cardinality. Okay? Now is definitely the time for questions, so please ask them if you have any. So remember, the Schroeder-Bernstein theorem says that if there's a surjection going both ways, I can conclude that these sets are of the same cardinality. And I was able to show that there's a surjection going both ways, so these sets are indeed the same cardinality. Now, I'll wait a second in case there are any questions, but if not, I'm going to move on to the next big thing. All right, seems like everyone's good with it. So what I'll leave you with today is something very odd. Many people have done videos about this, so you may have seen it before. We were able to conclude that the naturals, the integers, and the rationals all have the same cardinality, right? So these are all countable. Which kind of makes sense. I mean, it feels as though a lot of people have a visceral sense that there should only be one size of infinity. I mean, after all, the natural numbers is an infinite set, the integers is an infinite set, and the rational numbers are an infinite set, right? So it feels as though these are all, it seems like every infinite set that we encounter should have the same cardinality as the natural numbers. And people believed this until Cantor showed up and was able to show the following. So if you take all the real numbers between, say, 0 and 1, this is not countable. Okay. So this is the first example of an infinite set, I believe, that was shown to not have the same cardinality as the natural numbers. Okay. So this led to the observation that there are actually different sizes of infinity. Okay. The natural numbers and the real numbers between 0 and 1 do not have the same cardinality. Okay. Why is this? All right. So why do the natural numbers and real numbers have different cardinalities? You know what? It seems like people are bouncing. So maybe I've got on for too long. We can talk about this next time. So I hope you guys enjoyed the stream. Thank you so much for showing up. I do appreciate it. Leave a like if you enjoyed this. The VOD will definitely be put up. And also, if you could let me know in the comments how long you would like these to be. Because, of course, I don't know, honestly. I could go forever. Like, I have I have a lot of math capacity. But I know most people are not perhaps like that. So let me know how long you feel like these streams should potentially be. Do take a second to try that exercise. Also, let me know if you hate exercises. I noticed like the minute I assigned that, like 10 people left. So maybe no one wants to do. Maybe no one wants to get assigned homework by a streamer. So let me know if that's the case. Thank you all so much for coming. Let me know how the exercise goes. And also let me know if you hate exercises. Yeah, maybe I will put them up as videos. Let me know how you feel about this format. Anything that you want me to change, I'm more than happy to take a look at, or any topics you want me to cover, I'm happy to cover. All right, I will see you guys next time. All right, see you later. Peace.